Hello everyone and welcome back. Today we're going to continue our exploration of linear programming and focus on the theory associated to the processes that we've been discussing, which is going to really motivate and actually set the foundations of some of the important algorithms that are used to solve linear programming problems. So let's just briefly go over some of the basics that we've talked about up to this point. In particular, linear programs usually have three components associated to them. They usually have an objective function for which we seek to optimize. So let's assume we're interested in optimizing the functional g of x is equal to ctx, where c and x are both vectors. So there's our objective function, subject to some constraints. And let's assume we actually have three general family of constraints. Let's call it a sub l, x is less than or equal to b sub l. A sub g, x is greater than or equal to b sub g, and a sub e, x is equal to b sub e. So you have a bunch of different equations and inequalities relating your decision variables x1, x2 down to say xn. That could be in any of these forms, less than or equal to, greater than or equal to, and equal to each other. And let's assume we have the restrictions or lack thereof for the decision variables. In particular, we have our positive restraints, our negative constraints, and then our undeclared or our unrestricted constraints, xu, where xu union xn union xb should be equal to the entire vector x. So that's a linear program and its components. Now, what we did last time was describe a few computational tricks that one can do to write these in what we call standard form. So we were able to at least justify that all linear programs can be written in what we refer to as standard form, where the standard form of a linear program is one of the following structure. We seek to minimize our functional f of x is equal to ctx, subject to ax is equal to b. Here, a consists of all of our columns and all of our rows for our decision variables x. All our x's are there, all our b's are there as well, with restrictions. So for this, everything has to be declared, everything has to be restricted, and in particular, everything has to be restricted in the positive sense, right? So once you convert that original linear program into this, then that's what we call a standard form linear program. Now let us introduce the first theoretical construct that we're going to be using to discuss the theory of linear programming, and that's what we call a closed half-space. So a closed half-space is a set of the form H is equal to the set of all vectors x in the vector space Rm that satisfy the equation ATX is less than or equal to some constant beta, right? So that's going to be a set of vectors that satisfy some inequality. Now, one could define a closed half-space of either being of this form or greater than or equal to form. Either one of those would be perfectly fine, but one can show that one can express the greater than or equal to as a different version of this particular set H. Now, what exactly is a half space? So let's give a couple examples. So one example of a closed half space would be the set consisting of all the vectors that satisfy x1 is greater than or equal to 0. So what does that set particularly look like? Well, that set, at least in R2, so let's assume that x1 belongs to R2, is going to be the set of all vectors belonging to this region here, including that particular line there, right? So this would be the closed half space that is described by that particular relation. Is this the only half space? Of course not. There's quite a few other half spaces you could consider. For example, you could consider the half space x2 is greater than or equal to 0. So what half space does that look like? So again, if we're working in R2 again, that's going to be this set here, right? So that's the half space described by that. Keep in mind it has to be greater than or equal to, not just greater than. That would be an open half space, and open half spaces is not going to give us what we want for linear programming. Now, can you have other types of half spaces? The answer is of course yes. For example, consider the half space defined by the relation x1 plus 3x2 is less than or equal to 15. And let's assume, of course, that this is embedded within R2. So what does this half space look like? So one can find that if this is the x1 axis and this is the x2 axis, then 5 is going to be the vertical intercept, 15 is going to be the horizontal intercept. Our line of interest is going to be, well, it has to pass through those 2 points, of course, right? So that's going to be that. And then less than or equal to 15, that's going to be the downwards version, right? So this would be our half space, again, H. So why do we call it a half space? Because it pretty much breaks our space, Rn, into two pieces. In this case, the lower half, that's going to be our H, and then the upper half, that's going to be H complement, which is going to be that upper half piece, right? And also keep in mind the orange in this picture is not a closed half space, that's a open half space. If you want that orange to be a closed half space, you have to include that line defined by that relation, right? Because if we do not highlight that, that's an open line, which means it's an open half space, right? So that is what a closed half space is. Now let's define another term that you may have encountered in, say, pre-calculus. So definition number 2, a hyperplane. A hyperplane is a set of the form H is equal to x, again, belonging to some vector space Rn, such that ATX is equal to beta, with the restriction that A is not the zero vector and beta is a real number. So for example, let's assume that a hyperplane is embedded in, say, R3, and we want to graph, for example, 3x1 plus 2x2 minus 5x3 is equal to 4. Key here, notice that this is equal to, it's not less than or equal to or greater than or equal to. Those would be closed half spaces in R3. So this would be a hyperplane or a three-dimensional hyperplane, or a 3D plane as some people would say in R3. So what would this region look like? So of course, if this is, some axis here, I'm not saying that this is the x1, x2, or x3 axes, but nonetheless, this set is going to be some plane embedded in R3. So let's assume that this is a subset of, say, R3. The x1 axis could be there, the x3 axis could be there, and the x2 axis could be there. I'm not trying to draw this for accuracy here. We're just trying to get a sense of what we're actually looking at here in terms of terminology. All right, so that's the second concept that we have. So we have closed half spaces and we have hyperplanes, and they do not need to be two-dimensional, three-dimensional. They could be multi-dimensional, like 15 dimensions if you really want it to be. So our next concept that we need is the following. So suppose that H1 and H2 are both half spaces in the same vector space Rn. So you can't have one H1 to be in R2 and H2 to be in R6. You can't have that. Then the intersection of H1 and H2 is called a polyhedral set. A polyhedral set. And if the intersection is bounded, it is called, some people call it a polytope. A polytope, which in some sense is a polygon in n-dimensional space. So let's get a two-dimensional sense of what's going on here. So let's assume we have our 2D space characterized by x1 and x2. Let's assume we have this half space here. All right, so let's choose this space here. So this is going to be H1. Let's choose another half space. It doesn't have to be similar in geometry, but it has to be a half space in some sense. And let's assume that this is H2. So where is the intersection of H1 and H2? So the intersection of H1 and H2 is going to be this region here, including the orange and green line boundaries. Right, so that is a polyhedral set. But notice it is not bounded, at least geometrically bounded below, because notice that these will extend towards minus infinity. So give me an example of, for example, a polyhedral set that would be a polytope. So for example, let us consider a few half spaces because if we have h1, h2, and say h3, right? So let's assume that we have h1 there, h2 there, and let's assume h3 there. And let's assume that this is the intersection of those half spaces. Then that would be, for example, h1 intersection h2 intersection h3, which would be a bounded polyhedral set and hence would be called a polytope. Now, there's one other concept that we need to define here in particular. So let's go down here and define it. So definition number 4. So a set S in Rn. So S need not be a half space. S can just be any type of set. Is said to be convex if for any points x, y in S, the following always satisfies. Tx plus 1 minus ty also belongs to S for any t belonging to 0, 1. Right? So if x is a point and y is a point, if t is a real number, that means that is also a point. And if the set S is said to be convex, then this has to also belong in S for all numbers t belonging to 0, 1. So that may be a little bit abstract, at least to the new beginners in the theoretical math world. So let's draw a couple two-dimensional pictures to sort of demonstrate what it means for a set to be convex. Right, so example 1. So let's assume we have this little egg-shaped set. So let's assume that this is S. Let's pick any 2 points, for example, x here and y here. So is S a convex set? So pick any 2 points, and it has to be true for any 2. So this one can show is the equation of a line. So for example, when t is equal to 0, notice that x disappears and we're just left with y. And when t is equal to 1, notice y disappears and we're at x. So what this does is it traces from y into x. And notice that every single point along that line, at least in this picture, also belongs to S. And you should be able to see that that's actually going to hold for any 2 points that I choose. For example, I could even choose these 2 points here along the boundary. For example, if I choose that to be y and that to be x, then that line will always be within that set S. Now, can you draw an example of a set that's not convex? For example, let's assume that we have that type of shape. And for example, if I choose these 2 points, then the line connecting them will also be in that set. But for example, if I choose that point there and that point there and I connect them with the line, for example, if I choose x and that's y, then notice that these points here are not in that set S, right? And you could even choose, for example, this point Z, and that has to be a line, not a curve, right? So yes, sometimes this line is in the set, but it has to be in the set for all values t within 0, 1 for any 2 points x and y that you choose in that set. So this set on the left is convex, and this set on the right is not convex. Right? So that's just some ideas of what it means to be convex and not convex, at least in the R2 sense, but you could sort of generalize this geometrically up to higher dimensions if you want to. Now let's start introducing some theorems that are going to be extremely helpful to us. The first is this. Consider the half space H given by CTX is less than or equal to some number beta. Then one can show that this set H, this half space, is indeed a convex set. So let's sort of think about this from the two-dimensional perspective, and you can try and prove it for the general case if you desire. So if we choose any half space H in R2, for example, so let's assume that this is our half space H. If we were to choose any 2 points within this set and connect them, then that line will always be in that particular set. Probably the most extreme thing that you would have to check here is, for example, 2 points along that boundary, but since that boundary is indeed a line because it is a half space by definition, then that line will also be entirely contained in that particular set H, in particular along the boundary of it. So one should be able to show that any half space in Rn is actually indeed a convex set. The second theorem is the following statement. So if S1 and S2 are convex sets, then the intersection S1 and S2 are also, or is also a convex set. Again, I'm not going to prove it here, but I'll give you sort of a tour in 2 dimensions of sort of what we're talking about here. So let's assume we have a convex set here. It's not a linear convex set, but it's definitely a convex set nonetheless. And let's assume we shade that there. And let's assume we shade this. Let's assume that that is, of course, another linear or circular convex set. And then the intersection would be this little region here. All right. So notice that if we sort of shade these, that set shaded in red is indeed a convex set, but one could of course extend this to any convex sets in n dimensions. Now, how can we sort of combine these 2 theorems into some theorem that we can actually use? So theorem 3. The feasible region, let's call it F, of a linear program is a convex set, right? So keep in mind, if we're working with linear programs, this picture isn't going to make any sense because they're not linear regions, right? That would be a non-linear program, which we'll definitely talk about a little bit later. But the feasible reason F of a linear program is a convex set. And why is that the case? Well, every linear program can be written as an intersection of closed half spaces, and since the intersection of closed half spaces is indeed a convex set, that means the feasible region of an LP is also a convex set. Right, so that's just some idea of what we're talking about there. And if we sort of want to get a graphical sense of what's going on there, probably the most common one would be, for example, let's assume that this is our feasible region. Notice if we connect any 2 points within that region, even along the boundaries, then that would, of course, satisfy the criteria for being a convex set. Now let's introduce another definition that we're going to need to sort of expand upon these ideas, so definition 5. So suppose that x1, x2, all the way down to, say, xm, and let's assume all of them belong to Rm, then a convex combination, so a convex combination, some people will just write that as CC. If you're familiar with linear combinations, convex combinations are a similar thing, but it mandates convexity of the xk's is given by the following expression: t1x1 plus t2x2 all the way down to tmxm, where the tk's, the sum from k is equal to 1 to m of tk, must be equal to 1. Notice that in the definition of a convex set, between 2 points x and y actually satisfies this definition. Because remember, we had tx plus 1 minus ty, where again x and y belong to Rn. This is a convex combination of x and y, because the sum of these things, call that t1 and that t2, the sum of those are equal to 1, because those t's are real numbers. So I guess we should put that there. So these tk's must also belong to the set of real numbers. All right, so that's what we call a convex combination. Now, this next definition is going to be extremely important because it's going to start leading us into some theory for the solutions of linear programs. So let's let S be a region in Rn, and let's assume that this region also be convex, and let's choose an arbitrary point within that set. And then X is said to be an extreme point an extreme point of S if it cannot, keyword here, cannot be expressed as a convex combination of other points. Keyword here, other points in S. Okay, so let's look at a two-dimensional perspective of sort of what's going on here. So what exactly is a extreme point? So let's consider the classical feasible region for two constraints with two restrictions. So where would the extreme points be here? So one can ask, well, is this an extreme point? Well, can it be represented as a convex combination of two other points? Yes. For example, you could choose this point here, x, and that point there, y, and connect them, and there would be some number t that would sort of parameterize that point along that line. Therefore, that purple point is not an extreme point. But if you sort of pick this point there, is that an extreme point? The answer would be no, because for example, you could choose that point and along that boundary, and that would be a linear convex combination of, for example, that point x and y. Now, question, would this be an extreme point? Well, if we were to try the same exact trick, notice you would have to pick a point there and there, right? But keep in mind that that does not belong to our data set S. So one can find that that is actually an extreme point of this particular data set S, and one could also show that that point, and that point would also be extreme points in S. So as a corollary, at least geometrically, one should be able to show that corner points of convex sets, so corner points of convex sets are indeed extreme points, right? And that's actually going to be a very, very important result later on down the road. This next theorem that we're going to be looking into is where everything sort of starts to come together, including how linear algebra can sort of play a part in helping us solve linear programs. So let us suppose that you have a linear program that has already been placed in standard form, if it wasn't already, and let's assume that you've already classified the feasible region F to be the set of all vectors x and Rn's that satisfy Ax is equal to b, right? Where that's the constraints of our standard form linear program, and that's of course the restrictions of our linear program. And we also mandate that this feasible region be non-empty. That means there has to be at least one point in our feasible region for this theorem to be applied. So then if a point belongs to the feasible region, then we say that it is an extreme point if and only if, right? So if it's an extreme point, then this holds, and also if this holds, then that means it's also an extreme point. It goes both ways. Then the columns of A, the matrix, corresponding to positive components of X, must be linearly independent from one another. Okay, so lots of different things going on there. So let's look at a nice numerical example to sort of bring it together. So let's assume we have the constraints given by x plus 3y is less than or equal to 15, 3x plus 2y is less than or equal to 20. So you should be able to generate the feasible region at least in two dimensions for this particular region. So you should be able to show that this is going to be the sort of the shape of what we're looking at here, with a few points of interest. So definitely be able to know how to find these points. For example, 0, 5, 30 sevenths, and 25 sevenths. And this point here would be 20 thirds, 0, and that would be the origin 0, 0. And let's just shade the feasible region. So that's going to be our set F. All right. So if we were to write this set of constraints in standard form, how would we do that? So since we're working with two less than or equal to simples, that means we need to introduce two slack variables into the equation. So we're going to have, and let's also write x as x1 and y as x2, since we're introducing more than two variables here. So that's going to be x1 plus 3x2 plus, let's call it, say, s1. So let's call it s1 is equal to 15, and 3x1 plus 2x2 plus s2, so the slack variable for equation 2, that's going to be equal to 20. And therefore we can write this in matrix form to be, for example, in augmented form. A is equal to 1, 3, 1, 0, 3, 2, 0, 1, augmented with 15 and 20. So if we look at the reduced row echelon form of this particular coefficient matrix for our standard form of our linear program, then one can find that the reduced row echelon form for this is going to be equal to 1, 0, 0, 1, so the identity matrix in the bottom left-hand corner. And then we're going to have negative 2 sevenths, 3 sevenths, 3 sevenths, negative 1 seventh, augmented with 30 comma 7, or 30 over 7, and 25 over 7. So clearly we have a rank of 2 and a nullity of 2, so therefore we have 2 free variables and 2 fixed variables. But there's something very, very interesting here. So if we sort of look at this from the matrix form, because we need to, for example, dot product that row with, for example, x1, x2, s1, s2, that's going to correspond to what? So remember that this first column corresponds to x1, that second column corresponds to x2, therefore x1 and x2 are independent columns from each other, and we clearly see that s1 and s2 are dependent on columns 1 and 2. So when we look at our decision vector x, which is again x1, x2, s1, s2, the only two vectors that appear to be variables that are independent of each other are going to be x1 and x2. But look at what we have here on the right. Does that point look familiar? It should. That is particular, that point in the corner, right? Which we've already deemed to be an extreme point, right? Now, is that by chance? The answer is no, actually, because that's pretty much what our theorem is actually going for here. So x is an extreme point, in particular this is one of the extreme points, right? We have a few other extreme points, for example, 0, 5, 23rd, 0, and 0, 0 that you could actually generate from this particular world. And how would you do that? So if we actually look at the columns of 1 and 3 instead of 1 and 2 in the first two columns, and then reduce row echelon form that, and then do a couple other permutations, you actually can generate those other 4 corner points if you sort of do some column swaps within your augmented coefficient matrix, right? But we'll get into why that is the case in a little bit later. But notice that we can actually get our corner points and hence potentially our solutions to our linear program by looking at the independent columns and the solutions that they generate from the systems of equations where we have written our linear program in standard form. Now the next definition definitely has quite a few components going on within it, so let's break it down one piece by one piece. So we say a vector x, which belongs to the feasible region of a linear program, is said to be a basic feasible solution, right? So what are we looking at here? So we're looking at the set of feasible solutions, and we're trying to classify those feasible solutions as possibly potential solutions to our linear program, right? So this term pretty much leads into that idea. So we say that a feasible solution is a basic feasible solution if there is a partition of the matrix A into a non-singular square matrix B. So we're introducing a new matrix B, and this matrix B actually has a name. This matrix B is known as a basis matrix. So this is known as a basic matrix. And if you, for example, select columns 1 and 2, remember they correspond to some variables, right? So those variables for which are associated to that submatrix B, which we call XB, this is referred to as the basis variables. Right, so let's look at pretty much what we have going on here. So for example, if we have 1, 2, 3, 4, 5, 6, 7, 8, right? So let's assume we're choosing those two particular vectors, right? It is a square matrix, therefore x1 and x2 are going to be the vectors that are belonging to xb, and 1, 2, 5, 6 is going to be the matrix B. Now once we chop off that particular matrix, we're going to have, and let's actually include a couple other rows here. Let's do 9 and 10 as some additional columns. So once we chop off that little matrix B, right, that's that matrix B, we're going to have a potentially non-square matrix N there. And this matrix N is going to have a name. So N is going to be called the non-basis matrix. So the matrix A is partitioned into basis matrix and a non-basis matrix. And there's some variables associated to that non-basis matrix, right? Because that's going to be x3, x4, and for example, x5. So those are going to be our non-basis variables. So let's give that a name. So that's going to be x sub m. So this will be our non-basis variables. And it's very important that this matrix B, for which we've constructed, is non-singular. That is, the determinant of that matrix B cannot be equal to 0. So if we look at the determinant of that matrix that we have here, that's going to be 6 times 1, which is 6, minus 10, which is not equal to 0. That means that is a valid basis matrix for which we can select. So if that vector x, well, how do we define this basic feasible solution x, right? So that basic feasible solution x is pretty much a solution to this particular equation here. So x again is going to be xb, xn. So that's the union of the basis and non-basis vectors. And clearly xb has to be greater than or equal to 0. What we're going to do is we're going to define xn to be equal to 0. So x3, x4, x5 in our example is going to be defined to be 0. And x is going to be the solution to that resulting equation. Okay, so what exactly will that look like for, a nice general example? Let's actually use the same exact example that we had before because we actually already know where the extreme points are. So remember that the matrix that we had before was 1, 3, 1, 0, 3, 2, 0, 1, augmented with 15, 20. So what we're going to do is we're going to be letting B, our basis matrix, be columns 1 and 2. So 1, 3, 3, 2, which is non-zero. That means XB is going to be the vector containing x1 and x2. So if we choose B to be columns 1 and 2, that means our non-basis matrix is going to be column 3 and 4, which is 1, 0, 0, 1. And again, that doesn't have to be square, but our non-basis variables are going to be x3 and x4, which are technically our slack variables, but I'm just going to name them x3 and x4. So what we're going to do is we're going to choose x3, x4, which again is going to be xb, to be equal to the 0 vector 0, 0. Right? So once we do that, that means b, xb is equal to b, should satisfy. That means xb is going to be equal to b inverse times b, right? So what exactly is that going to be, right? And that's not xb, that should be xn, our nullity vector, right? Because that's what it was with our initial solutions. Okay, so xn is chosen to be equal to 0, and this should satisfy. And B again is our basis matrix. So remember, if we have our B chosen to be this nice little 2 by 2, we actually have some tricks to find the inverse of that 2 by 2. So B inverse is going to be equal to minus 2 sevenths, 3 sevenths, 3 sevenths, and negative 1 seventh. Our column vector B was again 15, 20. That means xb is going to be the product of the inverse of b times b. We already know that the inverse of b exists because the determinant of b is non-zero. So you can find that xb is going to be equal to, again, 30 sevenths and 25 sevenths, right? Does that look familiar? It should, because that's the same exact corner point that we investigated before. Now, is there other basic feasible solutions that one may generate, right? Because notice for our basis matrix B, we selected columns 1 and columns 2, which are indeed independent, right? But could you choose some other columns? You definitely can. So let's actually work through one of them. So let's choose columns 1 and column 4, right? So there are other B's one could choose, right? So we've already chosen B to be equal to column 1 and column 2, right? And that gives us a very familiar solution. But now let's actually let B be equal to column 1 and column 4 and sort of see what that leads us to. So that's going to be 1, 3, 0, 1. And that means the nullity matrix is going to be equal to C1, C3, which is going to be 3, 2, 1, 0. So again, this matrix is invertible. The determinant of that is just equal to 1. So what are our vectors for xb? So xb is going to be equal to x1 and the last slack variable. And also xn is going to be equal to x2 and x3. So what is the associated basic feasible solution for this selection of b? So basic feasible solution xb is going to be equal to, again, b inverse times b, which is going to be the inverse of the matrix 1, 0, 3, 1 inverse times our column vector b, same column as before, 15, 20, and that's going to be equal to 1, 0 minus 3, 1 times 15, 20, which multiplies down to 15 minus 25. So that means 15 minus 25 is another basic feasible solution, right? Now, question, is this really a basic feasible solution? Well, one can ask, well, is this really a feasible solution? So remember that we mandated that our slack variables be non-negative, right? Because keep in mind, that's x4, that's x1. Yeah, x1 is greater than or equal to 0. That checks out, but x4 must be greater than 0, and that's violated, right? So since this violates our restrictions, that means this particular b is not actually an extreme point for our particular value, right? So basic feasible solutions pretty much lead into extreme points, but not always, right? So if we were to drop all of our restrictions, then that would indeed be a possible basic feasible solution, but it's not in our feasible set based upon our restrictions, therefore it doesn't count. But you could work through all of our other combinations of columns, and you would actually generate the other three corners if you want. So again, let's sort of get some theory going on here. So let's assume we have an m by n matrix, right? So keep in mind this is n columns, m rows and n columns. We're selecting columns, right? So the number of basic feasible solutions is going to be equal to what, right? So some people actually allow basic feasible solutions to not be feasible solutions, and that's perfectly fine, because sometimes we would like to drop those restrictions in the practical sense, right? So sometimes that negative 25 might be actually valid. Yeah, you might be able to not sell 25 objects, but maybe you can buy 25 objects if you're a business. Yes, you lose money, but sometimes that optimizes some particular structure that you're actually working with. So how many columns do we need to select, right? So we have at most n columns that we're working with, but they have to be m by m matrices, right? So the number of basic feasible solutions that we have is going to be, of course, a combination, because column 1, 2 is the same as column 2, 1, so the order doesn't matter. So that means that's going to be an n choose m combination, which we should know to be equal to n factorial times n minus m, the quantity factorial. Right? But keep in mind, although these are the number of basic feasible solutions, we have some restrictions that could imply here. So let's just actually mention that formally here. But for each B generated, we have a couple scenarios that may come up. For example, B inverse may not exist, and 2, B inverse times B may contain negative entries, right? Which leads us into our next theorem. So theorem number, I believe, 5. So the set F, which again is going to be the set of feasible solutions, so x belongs to Rm, x equals b, x equals 0, so our standard form. It will have at most C and M extreme points. At most, right? Because once you violate those particular things, then that sort of gets rid of those, things that you shouldn't consider when you're talking about the solution of a linear program. So now that we have that, now that gives us practically all the tools that we need to state, for example, our last definition and also the last two theorems that pretty much lay down the entire foundation of what we're actually going to talk about next in this series. So let's again consider our basic feasible solutions, and let's call them X, and let's assume that they belong to the feasible region F, right? So in some sense, we're looking at the corner points or our extreme points of our region. So we say that a basic feasible solution is degenerate if at least one of the variables in XB is equal to 0. So if we think about that from our geometrical perspective, right, so we know already that that is a basic feasible solution, and so are those other 3 points. But notice that, for example, that point and that point, one of those variables is going to be 0. And in that basic corner point there, that's actually going to be both equal to 0. So these points there are what we call degenerate basic feasible solutions. And this point there, since it's entirely positive or contains all positive entries in its representation, is what we call a non-degenerate basic feasible solution. Okay, so those are just some common concepts and terminology that you may encounter in your discussion. Because if you have that, well, I don't have to sell any donuts in order to maximize profit, then why sell donuts at all, right? So one could sort of have that argument. That's sort of where degenerate and non-degenerate solutions sort of come into the conversation. Right. So with that in mind, let us introduce this next very important theorem. Okay, so theorem number 6. This theorem actually sometimes has a nice little name. It's called the resolution theorem. So it goes like this. So let us assume F is the feasible region, and again it's characterized by x belongs to Rm such that x is equal to b, x is greater than 0, and let's assume it's non-empty, and let's assume that this is a bounded set, right? So the feasible solution be bounded, so you can't have an unbounded set. Now, when we talk about bounded and unbounded feasible solutions, it's possible to have a maximum and a minimum for a unbounded set. For example, if we have, for example, this unbounded region, notice it does have a minimum. It's probably going to be located at one of those 2 points. And if you sort of flip that upside down, then that unbounded set would have a maximum, right? Or it could be having a max and a min, depending on if I draw this picture in some special sort of way. But let's assume for the resolution theorem that the feasible region is indeed a bounded set. And let V1, V2, down to say Vk, be the extreme points of the feasible region F, right? So let's assume we have a bounded region, and since it's a bounded region of half spaces, there should be a finite number of extreme points. Let's call them V1, V2 down to Vk. Then any x in the feasible region, extreme point or not, can be represented as a convex combination of the extreme points. This is a very, very important representation. So let's actually draw this from the two-dimensional perspective and see if we can sort of get some ideas of what's actually going on here with this resolution theorem. Right, so we have 1, 2, 3, 4 extreme points, and let's assume that we have this point there, right? So for example, how would I get to that point, right? So one could sort of think of it like this. For example, if I were to, for example, define T1 to go from there to there, T2 to go from there to there, T3 to go from there to there, and then T4 to go from there to there, then notice there exists a T1, T2, T3, and T4, all belonging to, for example, 0, 1, that will give you or generate that particular value or point within that convex region, right? So that, at least geometrically, that's what we're talking about here. So we can represent this point A as a convex combination of V1, V2, V3, and V4. There are several different geometry applications, especially in computer science, that sort of rely on the resolution theorem, which is actually pretty neat. Now, this next theorem really is the highlight of linear programming in terms of its application. So this is theorem number 7, which is sometimes referred to as the fundamental theorem of linear programming. The fundamental theorem of linear programming. So consider a linear program in standard form. So that's why we sort of focused on standard form a lot in the last video, because we need it for this fundamental theorem, so it's super important, with feasible region F. Then either, so 1, an optimal solution, for the linear program can be found at an extreme point of f, or, so what are we talking about here? So if we can find a optimal solution for a linear program, in particular, the extreme points are the only places you need to look for in terms of optimal solutions for the linear program. So that's why we actually only care about extreme solutions or corner points for a feasibility region. But if you cannot find an optimal solution to the linear program at an extreme point, that means the linear program is unbounded on our feasible region F. Right? That means if you cannot find an optimal solution for that linear program, that means the set you were working on is actually unbounded. For example, if you're trying to maximize, it's not bounded above, or it's only bounded below, or it's not bounded anywhere, or something like that. Right? And this is very, very important. That means what? That means if you are sure that you are working on the bounded feasible region F, which is of course an intersection of half closed spaces, that means the optimal solution always exists, and it always exists at an extreme point of that feasible solution. And those are some of the most important theoretical concepts associated to theoretical linear programming. So in the next couple of videos, we're going to be working through several applications and some very important algorithms associated to finding all of those extreme points for our linear program, and then trying to figure out which of those extreme points actually is our optimal solution, assuming that our linear program that we're working with is actually bounded. So I hope to see you there. Take care.